Okay, so we are going to talk some more about energy bar charts or LOL charts, as I like to call them. And then, let's see, so we will go through this rest of this worksheet, and then the next class we'll do some reviewing, and then the class after that we'll take a quiz on all of the energy stuff that we've done the last, I don't know, week and a half, 2 weeks. So that's the plan at this point. Let me make myself a little smaller here. Maybe. There we go. All right. Now, I don't think I had this up there for all the classes. So you might want to write this down again if you've not been here. Regardless, you didn't hear this anyway. Here's what for the energy bar chart. Here's what you need to remember. Everything we have initial, all of the initial stuff, plus what goes in to the energy flow diagram in work has to be equal to everything we have final, everything we have over here at the end, plus what comes out in work. So, something to keep in mind is that work can be done to transfer energy into a system, but work can also be done to transfer energy out of a system. Oh boy, I had somebody knocking at the door. Hold on. I don't even know if I can pause this. I don't think it's pausing. I gave him a pass. He wants a pass for you to come back. I have to write a pass. I'm recording a video. Oh, it's not you. Yep. Thanks. Okay. Oh, where was I? Oh, yes. So, work can be transferred into a system, or work can be transferred out of a system. I mean, work can be, oh my gosh. Energy can be transferred into or transferred out of the system, depending on how exactly the work is done. For instance, if I have something laying on the floor and I want to transfer energy to the object, well, I can pick it up, exert a force on it, and move it to a higher level. That's doing work and transferring energy into the system. I could also take that same object off of whatever the higher level is that it's on, and I could pick it up, and then I could lower it down to a lower level. I still have to exert a force to do that. Only the position change now is in the opposite direction of the direction I'm pushing, which means it's technically kind of like negative work. I'm transferring energy away from the object by doing that work. So both of those could happen, and maybe we'll see one of those happen later on in these examples. So anyway, back to the task at hand. Scenario number 3, we have a car moving up a hill, coasts to a stop, up. I don't know what that, up, yeah, like higher up on the hill. So at the bottom, what do we have? We have velocity that's bigger than 0. That's what that's telling us. It's moving. We have lines of motion there. Our y is height. Y represents height. So we have a height that is 0 at the bottom. No height, but there is motion, which tells me we don't have gravitational because we don't have height. We don't have elastic because nothing's been stretched or compressed, but we do have kinetic, and that's all we have. I personally would say 3 or 4 blocks. 3 or 4 blocks of kinetic. Oh gosh, I got the wrong thing on here. Oh my goodness gracious. I'd say 3 or 4 blocks. So, oh no, I gotta get my pen. Oh gosh. So we'll say 3 blocks of kinetic at the beginning. Now, at the end, what do we have? We don't have any velocity. We do have height. The height is now greater than 0 because the car went up. So as it was losing velocity going up the hill, it's losing kinetic, but it's gaining height. So that means it's gaining gravitational. By the time it gets to the top of the hill, all of what it has as kinetic is now height. It's not moving anymore, so we don't have kinetic. We do have height, so we have gravitational. There's still no elastic involved. So we have, I would say, 3 then blocks of gravitational. All of the kinetic we had at the beginning in the movement of the car became height because it was rolling up the hill. Some folks were asking in class about this. Well, hasn't any of that energy been internalized in the particles of the system moving around and friction in the car between the tires and the road? And well, yeah, I mean, in real life, there's going to be some internalized energy here. So, I mean, you could say, maybe there's a half a block of internal. And then, so take a half a block away from your gravitational, because maybe it didn't roll up the hill as far as it could have gone, didn't go up as far as it would have if some of the energy hadn't been internalized with the moving of the particles in the system. So I would say this could be acceptable. Again, there's more than one right answer to these. So it's about interpretation. Now, something that I would be probably wondering what exactly you were thinking. If you had most of it internal energy and only a little bit of gravitational, I would be suspect of that. That doesn't seem right. Or if you included kinetic in the final, or if you included elastic in the final, I would wonder what's happening there, because we don't have motion at the top of the hill. We don't have any springs or things that are wound up and compressed. So there are some things that are just plain wrong in this scenario. But the things that could be correct, there are several ways that you could interpret it in terms of how you divvy things up. I hope that makes sense. Moving on. Number 4. So now we have a person that pushes a stalled car to get to the service station. They don't call them that anymore, but get into the service station so that the car can be serviced, like put gas in it and whatever. So initially, what do we have? Is there any movement initially? Is there any kinetic? No motion lines. Motion lines, no motion lines. Any height? No. So nothing. Do we have anything stretched or compressed? No. Nothing. We have none of these. None of them. However, we do have a person involved, and it says a person pushes a stalled car. That seems like work is being done. Is energy being transferred to the car in this process? It sure seems like it, because the person is pushing it, and we see eventually the person and the car are both moving at the end. So it seems like work is being done, transferring energy to the car. So I would do something like this. Oh my gosh, I'm going to do this again. I would do something like this. Maybe there's 4 blocks of work being done. 4 blocks of work being done into the system. And again, the work is resulting in the car gaining energy. Now, what's the evidence of that? Well, it does say the person pushes the stalled car, and the car seems to have moved, and it's moving currently. So, do we have kinetic at the end? Yeah, because the car is in motion. Has the car gained any height? No. Has something been stretched or compressed? No. So we don't have this, we don't have that. Is any of the energy been internalized to the system? I mean, if it's real life, then probably. But I kind of ignore that. I usually only use internal unless there's obviously something missing. If energy is obviously missing, then you have to explain it by saying, hey, there's been some internal energy here where the particles themselves have taken some of the energy by their own movement and jostling of the particles through, again, things like friction, which is thermal production. Where was I? So the simple answer for this one would be that all of the work done by the person becomes kinetic because it's moving at the end. So the simple answer would be this: all 4 blocks of work would be kinetic. That'd be the simple answer. The little more complicated answer would be, hey, some of what the person is doing is been internalized. Half block, full block. I mean, I don't care necessarily how much, but I would say it'd be a little bit compared to how much kinetic energy the car has. Most of the work has produced kinetic energy, in my opinion, and then maybe some of it is lost to this thing we call internal energy, or the energy in the particles of the system itself. I hope that makes sense. Moving on. Load of bricks. Oh, this happens all the time. I constantly see loads of bricks on springs getting shot up into the air. So, a load of bricks resting on a compressed spring is launched into the air. This tells us we have no height. Also tells us we have no velocity. However, we have a spring that is compressed. Compressed spring. So that looks like EEL. And I'm going to go ahead and max it out with 4 blocks. Why? Because that's all we have. Like, that's all there is here. It's just elastic. And it's not like we're going to be gaining elastic in the final. So I don't have to worry about going above 4 blocks. So I'm just going to say all 4 blocks are elastic in the initial. Now in the final, notice it also says 0 there. So that's like 0 height. So here, by the time it's up here, do we see movement? Yes, there's movement. So we have a velocity that's greater than 0. So we have EK. Do we have height? Yes, we have EG. Is there any energy still being stored in the spring? No, that's already been turned over. The elastic energy that we had at the beginning, stored, has now become kinetic and gravitational. Question is, how much of each? Well, I have no idea how high this thing's going to eventually go, and I don't really know how fast it is at this point. So I'm just going to say that it's an even split because I have no idea. I'm going to say that 2 blocks are kinetic and that 2 blocks are gravitational. Do I have any evidence to tell me that that's the way it should be? No, I'm just guessing. If you say there's 3 blocks of EK and only 1 block of EG, could you be right? Yes. If you say there's only 1 block of EK and 3 blocks of EG, could you be right? Of course. So again, the finer details of how this is going to work from this scenario, we don't know exactly. And so you can kind of divvy it up how you think. Now, if you're thinking there should be some E internal, okay, put some of that in there too. If you think that not all of the energy that the spring had has become moving energy and height energy of the block, then sure, then some of it maybe was internalized in the system to the jostling of the particles. I just kind of usually ignore that part unless I have to. Unless I have to use it, I'll ignore it. So again, I hope you're seeing that yes, there are some things that have to be a certain way, but then there's other things that's it's room for some interpretation. I hope you're kind of being able to figure out which is which. Number 6, well, now we have a crate that starts at rest, is propelled up a hill by a tightly coiled spring. What does the block have? What does the crate have down here? No velocity, no height. Is there a spring that's coiled? Yes, it says it's propelled uphill by a tightly coiled spring. So we must have some elastic energy in here in the spring. How much? I'll probably go full bore on it and say 4 blocks because I can. I mean, we have no movement and we have no height, and all we have is the spring. So I'll just say that all of the energy we have is elastic, and we'll go with all 4 blocks. Final. Does it have height? Or I should say, is it moving at the end? Yeah, its velocity is greater than 0. That's what that means. Velocity is greater than 0. We have lines of motion. So there is kinetic. Is there height? Yeah, we have gravitational as well. Is there any elastic left? No, there is no more energy stored in the spring. The spring has uncoiled and it has pushed. So the elastic energy has now been released. We don't still have it stored up. So no energy elastic. Now, do you think there's going to be some internal energy? Because not all of the elastic became kinetic or gravitational, because maybe there's friction forces that are acting on, the block or the crate as it goes up. Well, sure. I mean, sure, that's a possibility. I probably will ignore it because we don't have any direct evidence that energy is missing. But you could say that there is some. Now, again, how are we going to determine how much kinetic versus how much gravitational? I don't know. Some people think that that's pretty high, so maybe there's not as much motion left. Like on this one, there was 4 lines of motion, so maybe that meant there was more kinetic. This one, there's only 2 lines of motion, so maybe that means there's more gravitational, less kinetic. Yeah, whatever. I mean, it's up to you. I would probably just still say there's half and half. Half kinetic, so 2 blocks of kinetic, and then half gravitational, 2 blocks of gravitational. That's probably what I would say. Now, if you think that there's some E internal here, well, then you have to take some away from these and put that into E internal. So maybe take a half a block from here, take a half a block from here, and make a whole block worth of internal energy. The goal or the key is this. Everything I have on the left plus what's going in has to equal everything I have on the right plus what left. So 4 in, I have 3.5 plus a half, that's 4 over here. Here I have 4, I have 2 and 2, I have 4. Here I have 4 blocks here, I have 2 and 2, I have 4 blocks here. So as long as what you have at the beginning is the same as what you have at the end, then we're good. And there's 2 more. I don't even know how long this video is at this point. It's probably terribly long, but whatever it is, what it is. A bungee jumper falls off the platform and reaches the limit of stretch of the cord. So the cord is as stretched as it can get here. Here, the person's obviously standing on the platform. So initial, is the person moving at the beginning? No. Does the person have height at the beginning? Yes. Is the bungee cord stretched at the beginning? No, it's just hanging there. It's not stretched. No elastic energy. I know it says it's a bungee cord, but there's no energy in it yet. It's not been stretched yet. And there's no movement. So all we have is gravitational. And I'll say all of it's gravitational. And why would I say all 4 blocks? Because it's going to eventually turn into other stuff. And this person's not going to get any higher. Like in the after picture, the person's not going to get higher. So I don't have to worry about needing to save some space for more blocks of gravitational. It's just maxed out. Afterward, is the person moving? I would say no. When you've reached the limit of the bungee, you're done moving down, you stopped, and you're about to get pulled back up. So when, and it even says in the picture, V equals 0, no velocity. No velocity. We don't have any EK. Is there any gravitational? Well, technically yes, because the person's head is a little bit above the ground. And if the ground is our 0, then there's a little bit of gravitational that's left. Is there elastic? Well, yeah, now the bungee cord is fully stretched, max stretched. Do we have any E internal? I probably would say no. I just don't put it in there unless I absolutely have to. Unless it's clear we've lost energy, I usually don't say that we have internal. So I'm going to say it like this, that there's a little bit of EG, like maybe 1 block's worth, or maybe even a half a block. Maybe I'll say a half a block of EG. And then 3.5 blocks, oh boy, a little bit high, there we go. 3.5 blocks of EEL. So again, that's a total of what? 4 blocks. I got 3.5 of that, half of that, 4 over here, 4 here, 4 here. Whatever we have at the beginning, we have to have at the end. And then finally, Superman. So Superman stopping a speeding locomotive is pushed backward a few meters in the process. So the locomotive is the thing in question, the system in question. And so we see clearly at the beginning, initial, the locomotive has velocity. It seems like a fair amount. It is a locomotive. So do we have motion? Yes, we have kinetic. Do we have height for the train or the locomotive? No. Do we have elastic energy? No, this is not a spring. This is like probably a coal burning or a diesel burning locomotive. So we have kinetic. Seems like probably a fair amount, so I'll just max it out with 4. It's not going to get any faster. In fact, the locomotive's going to stop. Superman's going to stop the dang thing. So we're not going to have any motion at the end. And so then we look at the end. It's not moving anymore. It got crumpled up here. Oh, maybe there is some internal here. Maybe some of what happened here is some crinkling, some deforming of some stuff. So we have some E internal. However, we also have Superman who's pushing backwards, or who got pushed backwards as he was stopping the train. So was Superman exerting a force on the train? Did he take energy away from the train? Sounds like that is probably what happened. So was work done to remove or take away energy from the train? I would say. How much? I don't know. Maybe Superman did 3 blocks worth of work. Maybe 3 blocks worth of work by Superman, taking energy away from the train or the locomotive. And then maybe there's a block of internal because the train does look like it's kind of gotten wrecked a little bit. I mean, it looks like it's kind of bent and twisted a little bit. So maybe some internal energy within the system, but then Superman did some work as well. So between the two of them, maybe that's where the energy has gone. Now notice what happens here. We have 4 blocks of EK at the beginning. What came out of the system and what we have left in the system, between those two, we have 4 blocks. What we have at the beginning has to equal what we have at the end. That's the law of conservation of energy. All right. I hope that this at least this is maybe starting to make some sense. We'll do some more reviewing in the next class, and then again, we'll have a quiz after that. So hopefully this makes sense. Sorry the video is so long. Take care of yourselves. We'll see you.